This is my Precalculus course. Today we're going to study the concept that we know as average. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. The reason we're going to study average is it's an important topic in the math curriculum overall, but it's also very important when it comes to the study of calculus. Now, most people think that there's only one way to calculate an average value, but average is actually a general concept, and there's really many different ways to calculate the average. An average value is a number that is an estimate of a typical value among a group of numbers. So this is the general idea of average. It's a typical value. For example, if you think about the price of a loaf of bread, look at all the prices that you'll see in different brands and different stores. An average price would be what we would consider a typical price for a loaf of bread, which might be $4, maybe $5, somewhere around there. And so the average is an estimate of the typical value. The average is also usually the center of the data. So if you look at all the prices for a loaf of bread, the average would be the number that is somewhere in the middle of those numbers. It's not the smallest number, it's not the biggest number, it's right in the middle. So now let's look at the different ways to calculate a typical value. The most famous way is what we call the arithmetic mean. This is just a fancy way of describing what we usually think of when we talk about the average. You can consider the arithmetic mean the default method. If somebody tells you to calculate an average value, but they don't tell you the particular route that they want you to use or the method, you would assume that they're talking about the arithmetic mean. So that's very important, because sometimes you'll get problems where they give you an average value and you're just supposed to assume that it's the arithmetic mean. That's not very fair, but they'll do that anyway. And we'll talk about that more later. But the arithmetic mean is calculated by adding up all the numbers in a group of numbers and then dividing by how many numbers there are. So there's 5 numbers, 1, 2, 3, 4, 5. So we're going to divide by 5. And when we add up all these numbers, we get, let's see, 23 plus 36 plus 31 plus 38 plus 29 is 157. Divide that by 5, and we get 31.4. So this number is what we would consider a typical value that you would see in this list. Now, in this case, you don't see this number in the actual list. So you're probably thinking, well, wait a second, this is not a typical value because there's no decimals in this list, so how could that be a typical value? Well, it's considered a typical value because it's right in the center of the data. Again, that's another way to think of an average value. It's the number that's in the center of the data. Now, 100 would not be a typical number that you would see in this group of numbers, right? So 100 would not be an average value. 0 would not be a typical value because you don't see numbers that are close to 0 in this list. But this number, because it's right in the center of the data, you could say that that is a typical, or the most typical number that you would see. So again, it's just a measure of a typical value. So try number 2. We're not going to do a lot of these problems, and I'm calling this AM, which is arithmetic mean. So try number 2. When you come back, we'll do it together. All right, we're back. So we're going to add all the numbers together and then we're going to divide by how many numbers there are. It looks like there's 1, 2, 3, 4, 5, 6, 7. So if we add these numbers, we get 6, 9, 16, 26, 31, 35. So we've got 35 divided by 7, which is 5. Notice that 5 is kind of in the center of the data. The biggest number is 10, the smallest number is 2. So you would expect the average to probably be somewhere in the center, and 5 is somewhere near the center of the data. And it's also important to note that the number of occurrences that you see of a number, that gives that number more weight, and we'll talk about the idea of weights regarding numbers and occurrences of numbers later on. But if you got 5, good job. Again, that's a measure of a typical value. So again, the default method for calculating average is what we call the arithmetic mean. But there are other lesser known methods for calculating what we would refer to as a typical value. The geometric mean is an example of that. We're not going to do a lot of problems because this is not really a very common method. It's not really a method that you're probably even expected to know. But this method finds the nth root, n being the number of numbers. In this case, it's 6 numbers. So we're going to take the 6th root of the product of all these numbers. And the reason that this is considered a measure of the average value in a list is because it gives us a number that's right in the center of the data, a fairly good estimate of the typical value. And by the way, I don't know if I mentioned, but notice it says that the average is an estimate. Sometimes the average is a good estimate, sometimes it's not. So just be aware of that. It depends on the context. Now we have to enter this mixed number into our calculator. So I'm going to show you how to do that. If you're using a TI-84, let's calculate the product first. So 12 times 15 times 15 times 13. And I'll show you how to do this in your iPhone, even though you shouldn't be using your iPhone. Remember, they don't allow iPhones in school. But we're going to enter these numbers, but when we get to this number, if you want, one way to do this is to, instead of entering 12, you can press the green alpha button and then the stat plot F1 button at the upper left, which says y equals. Then you'll have a drop or a window pop up, and then you'll use the down arrow key to go to number 2, where it says UN/D. Press enter on that, and it'll give you a mixed number template. So it should look like this, and then you can enter that mixed number. So that's just that's a tip that'll be useful to you in as you go through the math curriculum using your TI-84 Plus. And then we can just say times 15.5, because 1/2 is 0.5. Enter, and we get the 6th root of 6,709,950. Now, we have to find the 6th root. Now, if you're using your iPhone, you can just enter 12.3333 and just keep entering 3s. It may not give you the exact number. If you're using your iPhone, you're going to push this button. It's the white root of X. That's right in the center if you rotate the phone to landscape mode. But if you're using a TI-84 Plus, There may be a different way to do this, but I actually don't know what that would be. Maybe somebody can research it for me, but the only way I know how to do this in a TI-84 Plus is to use the exponent button at the middle right under the clear button. And then you can push the alpha button, the green alpha button, and the y equals button, and then press enter on number 1, and it'll give you a fraction template. And then you want to write 1 over 6. So you want to raise that to that number to the 1/6 power. So if we do that, we get 13.7 roughly. So you can see that this gave us a typical value, a value in the center of the data. It didn't give us 100, it didn't give us 1,000, it didn't give us 5 or 2 or -18. It gave us a number that is very typical of what you would see here, and it's a number that is around the center of the data. Now down here you don't have 6 numbers like the previous problem. You only have 4 numbers, so we're going to find the 4th root of the product of those numbers. So I want you to try number 4, and when you come back we'll do it together. Okay, we're back, so we're going to find the 4th root of the product of all those numbers. So if we multiply all those numbers, we get the 4th root of 1,568. And so that's going to be roughly 6.29. I'm going to round to the nearest hundredth place, but you can round however you want to. So 6 is right in the middle of the data. The biggest number is 8, and the smallest number is 4, so you would expect the number to be around 6. The fact that 7 appears more than once does give it more weight, as we say. But if you got that number, good job. Okay, so let's now use the median to calculate average. Again, we're using more than one route. Average is a general concept. There's more than one way to calculate average. So the median is simply the middle number in a data set if we order the data set from least to greatest numbers. So the smallest number here is 47, the next biggest is 49, the next biggest is 50, the next biggest is 59, then 60, then 62. Now we're going to find the middle number, and you'll notice that there is no middle number, but we can find the number that's right in the middle of these two numbers, which would be 54.5. So one way that you can do that is by finding the arithmetic mean, add these two numbers and divide by 2. But another way you can do it is just figure out how far apart these numbers are. They're 9 units apart, and then just divide that by 2 and get 4.5. That's the same thing as the arithmetic mean, except we're just adding 4.5 to the smallest number. Anyway, I think you get the point. 54.5 is right in the middle. So the median is the middle number, quite literally the middle number. Now remember, the average is usually somewhere in the middle of the numbers, but the median actually is the exact middle value. So this can be kind of confusing sometimes to think of these concepts because they seem so familiar, and yet there are minor differences. Now, here we had 6 numbers, and there was no middle number, so we had to find a value that represented the middle number. Here you don't have to do that because you have an odd number of numbers. So try number 6. The number you're looking for is just going to be the number right in the middle of those numbers. But remember, you have to order them from least to greatest first. So try number 6, and when you come back, we'll do it together. All right, we're back. So we have to order these numbers from least to greatest. And then we're going to find the number that is right in the middle, which is obviously 18. That's the median. So the middle number is a good measure of a typical value in a data set. So we learned the arithmetic mean. That's one way of calculating an average value. We learned the geometric mean. That's another way of calculating an average value. And we learned the median, a third way of calculating an average value. But now we're going to use another way, which is called the mode. The mode is the number that appears most often in a data set. So for example, the number that appears most often in this data set is 203. So that is a measure of the center of the data. So because these numbers appear most often, they have more weight, and they're very representative of a typical value. Okay, so go ahead and find the mode, the number that occurs the most, in problem 8. If you said 1/3, you're correct. So this is an estimate of a typical value in this data set. It's a measure of the center of the data. Now you might say, well, wait a second. If you order these numbers from least to greatest, 1/3 is actually the smallest number in the list. So how can it be a measure of the center of the data? Well, the reason it's a measure of the center of the data is because 1/3 occurs twice, which means that it has more weight. These numbers only occur once each, so they have less weight. And that brings us to another important point, and that is weighted average. As long as we're discussing average, we may be good to go over weighted average. Weighted average is calculated by assigning unequal worth to numbers depending on the frequency of their occurrences, like 1/3 for example, or their perceived value. Now there's a lot of different types of problems relating to or using a weighted average, and I want you to be aware that sometimes these problems can be ambiguous, convoluted, and confusing. And so just be aware that things get kind of difficult sometimes when teachers are writing these problems. They tend to make these problems more confusing than they really need to be. I'm not going to do that, but I just want you to be aware that you're going to see some of those problems out there, possibly on college entrance exams and various standardized exams, and you have to prepare for those problems by taking practice tests and whatnot. But we're not going to get into the weeds in that right now. We're just going to learn the basic concept of weighted average. So now before we continue, notice it says average, but it doesn't specify what type of average. Remember, if the type of average is not specified, then we're supposed to assume we're talking about the arithmetic mean. That's the default average. So what we're going to be doing here is just calculating the arithmetic mean. The difference is the way that the data is organized that we're given. We're given this data, but it's organized in a different way than what you would see with these problems up here when we found the arithmetic mean. But it's really just the same problems. So let's read. It says, Bill sold hats, t-shirts, and buttons at the football stadium yesterday. Use the table below to calculate the average price per item of all the things that he sold. So I'm just going to call this AM because it is the arithmetic mean that we're about to calculate. So our instincts tell us to take these three numbers, add them up, and divide by 3. because that's how we calculate the arithmetic mean. The problem is these numbers don't have the same weight. This number 1 has much more weight than the other numbers because 124 of those buttons were sold. Let's use an extreme example. Let's say that he sold 1,000 buttons, but he only sold 2 hats and 3 t-shirts. If you sell 1,000 buttons and only 2 hats and 3 t-shirts, then are you just going to add these up and divide by 3? Well, no, because that number would be way too big. The typical value is going to be closer to 1 because the buttons are really what Bill is selling. He's not really selling hats and t-shirts, because if he only sells 2 or 3 hats and t-shirts, you can't say that those are typical prices for things that he sells, because he almost never sells those, right? That's the whole idea here. So we're not going to add those numbers and divide by 3, because if you do that, you're giving equal weight to all 3 numbers. So what we're going to do is we're going to add 5 16 times, because each one of these numbers represents a sale. And I'm not going to write it because it's not enough room. But then we're going to add 18 15 times, because each one of those numbers represents a sale. Then we're going to add 1 24 times. And then we're going to divide that sum by the total number of things that he sold, or the total number of sales, which is the sum of the numbers in this column. So that is the arithmetic mean. That's all it is. But because the numbers are organized differently, we call this the weighted mean, or excuse me, the weighted average. So because we don't have enough room to show the sum in an expanded form, we're going to just multiply 5 times 16 and 18 times 15 and 1 times 124. So this is the sum of all of the prices, the sum of all the numbers per item. And then we're going to divide by the total number of sales, which is 16 plus 15 plus 124. Now you can do this in your TI-84 Plus. Push the green alpha button at the upper left, then the y equals button at the stat plot F1 y equals button, then press enter where it says n/d. So we should have a fraction template now. So now we can enter the numbers in. 5 times 16 plus 18 times 15 plus 1 times 124. Press the down arrow key. 16 plus 15 plus 124. Press the right arrow key. And before you press enter, we want to make sure that we entered all these numbers correctly. So let's press enter. And we get 474 over 155. So that's kind of weird that the calculator gave us a fraction. That's because this TI-84 Plus is programmed to give us a fraction in this context. I'm not exactly sure why, to be honest with you. So in order to deal with this, we just enter 474 and then press the divided by button and then 155, and we get 3.058 approximately. So the arithmetic mean of those prices per item is $3.058. So we're rounding off a little bit. So that's the average price per item that he sells. So I want you to try number 10. Number 10 is very, very similar to number 9. So go ahead and attempt number 10. when you come back, we'll do it together. Okay, we're back. So again, we're going to find the arithmetic mean, and that is 20 times 4 plus 15 times 16 plus 18 times 8 plus 17 times 20. Then we're going to divide by the sum of all of the wheels that were sold. Now again, you can press the green alpha button, the y equals stat plot F1 button at the upper left. Press enter, you got your fraction template. And let's make sure that we entered everything correctly, or we wrote everything correctly, that is, before we do the actual calculations. There's a lot of stuff to write down. So 20 times 4 plus 15 times 16 plus 18 times 8 plus 17 times 20. Down arrow key, 4 plus 16 plus 8 plus 20. And before you press enter, we need to go back and check all the numbers that we entered into the calculator. It's pointless to do this unless you actually check. Students like to pride themselves on having speed, but speed means exactly nothing unless you write the expression correctly or enter it correctly into your calculator. So we're going to press enter, and we get 67 over 4. And if we enter 67 divided by 4, the calculator will give us the number in decimal form, and that is inches. So the average diameter is about 16.75 inches. Now, in these particular problems, are these numbers really useful to us? Well, they might be useful to us, they might not, but regardless, this is the concept of weighted average. So if you got that right, excellent. Be sure to write your units. Okay, so let's do one more example of weighted average. Now, this is an example that we'll find in science. Now, this is kind of an advanced topic here, but a lot of students do take chemistry courses, and chemistry is one of the three primary sciences. So this is a good example of something that you're going to be asked to calculate in a chemistry course, but generally the textbooks don't really explain the logic behind it. So we're going to do that. Now in this case we're given percents. So how do we deal with this? Well, let's read the problem. It says 98.9% of the carbon atoms on Earth have a mass of 12 AMUs. AMU stands for atomic mass unit. 1.1% of the carbon atoms have a mass of 13.00335 AMUs. So those are more, they have more mass. What is the average mass of the carbon atoms on Earth? So this is an example of weighted average because there's a lot more carbon 12, we call that carbon 12. There's a lot more carbon 12 on the Earth. There's 98.9% of the carbon is carbon 12. So this number has more weight than this number because this number represents only 1.1% of the carbon on Earth. Now there's a third type of carbon called carbon 14, but it appears so scarcely that it's not even worth really mentioning. So here's what we're going to do. We're going to take that percent and change it to a decimal, and then we're going to multiply by 12. We're then going to change the other percent to a decimal and multiply by 13.00335. And that's your answer. So chemistry textbooks will give you this calculation here, and they'll say, well, that's the average atomic mass. The problem is they won't explain what we just did there. So as long as we're talking about weighted average, let's just explain briefly what this means. So this is a percent written as a decimal, and remember, a decimal and a percent, they just represent fractions. So this number here represents the number of carbon-12 atoms divided by the total number of carbon atoms. So not all carbon atoms are carbon-12. So anyway, you divide those numbers and you get that decimal. And then we're multiplying by the mass of carbon-12. So that's that number. Then this number here is the number of carbon-13 atoms divided by the total number of carbon atoms. I know this is kind of convoluted, but I just want you to see that this is an example of the type of problems that you'll get where they won't even really explain to you the logic behind the calculations in some of these textbooks, but this is actually an example of weighted average. So we're not going to do this a lot in this class. In fact, I'm only going to give you probably 2 problems. It's not really something you need to worry about. If you don't understand the logic of what we're doing here, that's okay. It's not a big deal. This is not a big part of my curriculum. So then we multiply by the mass of a carbon-13 atom. All right, so that is the green number. Let me find some more room here. So why is this considered to be an average atomic mass? Well, believe it or not, this just represents the arithmetic mean of the masses of all the carbon atoms out there. But it doesn't look like it. So how do we explain this? Well, if you multiply these two, what you get is 12 plus 12 plus 12 plus 12 plus 12. There's, quadrillions upon quadrillions upon quadrillions of carbon-12 atoms. We can't even count them, but you're just adding up all those 12s and then dividing by the total number of carbon atoms. So when you multiply these numbers, remember, when you multiply a fraction by a number, you just multiply that number into the numerator. You don't multiply it by the denominator. So when you take the number of carbon atoms and multiply by the mass of each carbon atom, which is 12, we're just adding 12 however many times, or however many number of carbon-12 atoms there are. And over here, we're doing the exact same thing. We're adding 13.00335, then adding it again, as many times as there are carbon-13 atoms. And we're dividing by the number of carbon atoms, the total number of carbon atoms on Earth. So then we add these fractions together, and again, when we multiply the numerator and that number, we come up with the sum of all those 13.00335s. So we have a common denominator, which means that we can add these fractions together, and then we just get the sum of all of the 12s. We're going to add 12 as many times as there is a carbon-12 atom on Earth, which is a lot. And then we're going to add up 13.00335 as many times as there is a carbon-13 atom on Earth, and then we're going to divide by the total number of carbon atoms on Earth, and so that's going to give us the arithmetic mean of the masses, or of the mass of a carbon atom. So I know that seems really convoluted, and you don't really have to understand that, but that's just the arithmetic mean. So you need to be aware that this stuff can get really convoluted, especially when the textbooks don't explain this. So let's multiply 0.989 times 12, and we get 11.868, and then add 0.011 times 13.00335, and we get 12.011, and we have to write AMUs. So that is the average. So if you look at a periodic table, this is the number that's going to be written, probably 12.01, somewhere around there. So if you didn't understand that, that's okay. I'm just letting you know that there's all kinds of different contexts in which you can calculate an average. This seems like it's really a perplexing way to calculate an average, but all it is just the arithmetic mean. But we're using percentages, and it's considered a weighted average because of the numbers that were given. So I want you to try number 12, and when you come back, we'll do it together. Number 12 is going to be pretty much exactly the same type of problem, and you don't have to write all of this stuff here. You can just do this calculation and you'll be done. When you come back, we'll do it together. Okay, we're back. So the average atomic mass, which is the same as the arithmetic mean of the masses, is 0.1978 times 10.0129 plus 0.8022 times 11.0093. So let's do the calculation. Remember to double check all your numbers that we're entering into the calculator. It's very easy to enter a wrong number. So we got 10.8. 10.8 AMUs. So if you look at a periodic table, boron is number 5 on the periodic table, and you'll see 10.8. Probably say 10.81. We can carry out one more decimal there. So if you got that right, excellent. Okay, so now we're going to average rate of change. This is something that is particularly important for calculus. So remember, there are different ways of calculating average, and we're about to go into more examples of that. Again, we tend to think that there's only one way to calculate average, but it depends on the context and the algorithm that you're using. Here's a general definition of average rate of change. It's just the total change in one quantity divided by the total change in a related quantity on a particular interval. The average rate is a measure of the typical rate during an interval. So an example of this is the slope of a line. Remember, in my beginning algebra course, we graphed lines, and if you choose 2 points on the line with coordinates x1, y1, and x2, y2, The slope is a measure of how steep the line is, how fast y is changing in respect to x, in respect to the change in x. So here we have a perfect example of the average rate of change, the total distance, or the total change in one quantity divided by the total change in another quantity. Slope is an example of average rate of change. So we're changing y and then dividing by the change in x. So this is just a general definition, a general idea of average rate. But again, these definitions can get kind of ambiguous. There's not just one definition of average rate. If you consider the average speed is assumed to be the total distance traveled divided by the total time that is passed. And you can interpret this using this general idea, but it does get a little ambiguous as to how we're going to do this. You can consider the distance traveled to be 0 when somebody starts a race, for example, but then when a certain amount of time has passed, the distance total that has been traveled would change. So that's one way to think about this. So let's do an example. If John drove his car 1,200 miles during his 48-hour trip, what was his average speed during the whole trip? Well, average speed, which is an example of average rate, is defined to be the total distance that he traveled, which is 1,200 miles, divided by the total amount of time that passed. So 1,200 divided by 48 is 25. So the average speed during his trip is 25 miles per hour. Okay. Now, the problem with this is that John was not going at the same speed for the entire trip. Was he? I mean, obviously not. He had to stop for gas, right? When he was putting gas in his car, he wasn't moving at all. His speed was 0. At some point, he had to stop and get gas, and that required him to slow down. So during the time when he's slowing down, he's got a lot of different speeds. And so during this trip, he's not moving at the same speed. So the average speed is just a measure of his typical speed. So that would be 25 miles per hour if you give the various speeds that he's moving a particular weight depending on how long he's moving at that speed. So to demonstrate that, we go on to the next part of the problem. It says, during the trip, John stopped to sleep and eat. If he drove for a total of 20 hours throughout the entire trip, what was his average speed during the time that he was driving? You see, this is asking for the average speed for the whole trip, counting even the time that he was asleep or eating or getting gas. But in this part of the problem, it's asking for the average speed only during the time that he was actually driving. So the number is going to change. So we're going to take the total distance that he traveled and then divide by the total time that he was actually driving. And if we do that, we get a number that is much higher than the previous number. Why is that? Because the context of the problem changed. We're asking for something different. So here we have 60 miles per hour. Here we have only 25 because this problem does not count the amount of time that he was sleeping, eating, or getting gas. So these are typical speeds. They represent typical speeds over a certain interval. Again, the average rate is a measure of the typical rate during an interval. But do you see how the number changes based on what the problem is actually asking? So the general idea of an average value is pretty easy, but unfortunately, what I'm trying to demonstrate for you is that sometimes these problems can be more complicated than you think, so you just have to be careful. So let's do another problem. This is not going to be an average speed problem. This is just an average rate problem, because we're not actually traveling a distance necessarily. So it says, on Sunday, Casey spends 3 hours searching for coins and finds 22. On Monday, he spends 5 hours searching and finds 14 coins. He wants to know if collecting coins is worthwhile. To help him, he decides, to help him decide, he calculates the average number of coins he found per hour that he searched. What should this number be? So what we're going to do is use our definition for average rate. Remember, average rate is the total change in one quantity divided by the total change in a related quantity. So the total change is going to be that he found 22 plus 14 coins. So that would be a total of 36 coins. That's the total change when it comes to the coins that he has. He now has 36 more coins. That's the change. He may have had 100 coins, but then he found 36. Well, now he has 136. So the change in the number of coins is 36. Then we're going to divide by the total amount of change in the time. 8 hours have passed in relation to the time that he actually searched. So if we divide these numbers, 36 divided by 8 is 4.5. So he found 4.5 coins per hour that he actually searched. Now this is only including the time that he searched. So from the time that he searches to the time that he stops searching, he finds about 4.5 coins per hour. All right. But look what happens in this second part of the problem. It says Casey had to stay in a hotel for 3 days to search for coins. What is the average number of coins he found per hour over the course of the 3 days? Well, this is different. So the average rate is equal to the change in the number of coins that he found, and that's going to be, of course, 36, same number. But now we're dividing by the total amount of time, because, again, the context of the problem is different, and it wants the number per hour. So we have to take 3 and multiply it by 24, because there's 24 hours in a day, so there's 72 total hours during that 3-day period. And we get 1/2 coin per hour. So if we want to find the average number of coins he found per hour for the entire trip, it comes out to only 1/2 coin per hour. So if you include all the time that he had to spend to be in that area, he had to go to a hotel, rent a hotel, the whole time that he had to be there, if you include all that time in the calculation, then he only found 1/2 coin per hour that he was actually at this location. So is it worth it for Casey to go looking for these coins? Well, obviously it depends on the value of the coin, and only he can know that. But you see that these two rates are very different. the average rate for the time that he was looking for coins was 4.5 coins per hour, but the average rate over the course of his entire stay at this location was only 1/2 coin per hour. So again, the whole point of showing you this is that calculating an average value really depends on the variables that you're given, and unfortunately in many of these problems you're not really given a clear description of what is even happening in the problem, so you have to be careful. So let's do one more example. It says, during a race, Natalie ran 3 yards per second for 200 seconds. She then grew tired and ran the rest of the race at 2 yards per second for 100 seconds. So she slowed down. What was the average speed during the race? Well, remember, average speed is the total distance traveled divided by the total time that's passed. But this is actually a weighted average problem. It's still going to be average speed, but the way that we're going to calculate it is different because it's going to be a weighted average. So the reason that this is weighted average is because Natalie was running 3 yards per second for 200 seconds, but she was only running 2 yards per second for 100 seconds. So you can't put the same weight on these numbers. You can't take 3 and 2, and I just noticed that that should be written as a word. Sorry about that. So she ran 2 yards per second for only 100 seconds. So there's more weight on this rate than there is on this rate because she was running the faster rate for longer. So that's why this is considered a weighted average, even though it's really just the same thing that we calculated before. It's average speed. The algorithm that we have to use is just slightly different. So we need the total distance traveled divided by the total time. And we can use this information to calculate those numbers. Now again, this problem is convoluted. All you have to do is take the total distance that she ran and divide it by the total time that she was running, and you're done. The problem is it doesn't give us that information. So we have to do some calculations ourselves. So let's find the total time. Well, that's really easy. That's just 200 plus 100. So that's very easy. But the total distance, well, that takes a little bit of thought. Natalie ran 3 yards per second, meaning she runs 3 yards in 1 second. Think about this. She runs 3 yards in 1 second. But she was running for 200 seconds. She wasn't just running for 1 second. She was running for 200 seconds. So what is the total distance that she ran? She ran 3 yards in 1 second. But she wasn't just running for 1 second. She was running for 200 seconds. So how do you do this? Well, it's just 3 times 200. That's the total distance that she ran when she was running at 3 yards per second. Then she changes to 2 yards per second. That's her new rate. So in 1 second, she runs 2 yards. But she wasn't running for just 1 second. She was running for 100 seconds. So if you want the total distance that she ran during that time, you have to multiply those two. So this is the total distance that she ran during the second part of the race. So now you have the total distance divided by the total time that's passed. So that is the average speed. Now, is that convoluted? Yes, it's very convoluted. But again, I'm just warning you that these are some problems that you may see. So if we add these numbers, we get 800 over 300. And we don't really have enough room to write, so I'm just going to skip forward. We have 2 2/3 yards per second. So that's the answer. Okay, so this was an example of weighted average. Because we had to put different weights on these rates. We don't just take 3 and 2 and add them together and then divide by 2. That would give us 2.5. The actual average speed is 2 2/3, which is not the same thing as 2.5. Because again, she was running 3 yards per second for 200 seconds as opposed to 2 yards per second for only 100 seconds, you see. So you have to put different weights on the numbers. Okay, so I want you to try number 16. You can use number 14 to help you. They're going to be about the same type of problem, I believe. So try 16. When you come back, we'll do it together. Okay, we're back. So if you got that right, good job. Now, if you didn't get the units right, well, that's an important point. You have to make sure that you have the correct units. We're not calculating per hour, we're calculating per day. Okay, so you can get a picture of this information if you'd like to help you with number 17, and I want you to try 17. These two problems require average speed. The definition of average speed, which is the total distance traveled divided by the total time passed. So be sure you have that definition in front of you. Try number 17. When you come back, we'll do it together. Okay, we're back. Per minute. That's his average speed. So if you got that right, excellent. Go ahead and try 18. And this is another average speed problem. And when you come back, we'll do it together. Okay, we're back. Because we were given different numbers to find the average speed, it's called the weighted average, but it's still the same average. So now we're going to get into examples involving function notation. So in calculus, we define something called the average rate of change of a function. And let's say that we have some function f of x, which we've graphed. The red part is the graph of the function. And we want to find the average rate of change in a particular interval. The interval is usually described with the x value. So the interval is x1 to x2. The average rate of change is defined to be the change in the y values of those points divided by the change in the x values. So the change in the y values is y2 minus y1, and the change in the x values is x2 minus x1, and that's the slope of a line that goes between those 2 points, and we call that line the secant line. Remember, in my geometry course we learned that if a line touches the graph once, it's a tangent line. If it touches twice, it's a secant line. So the slope of the line going through those 2 points on the graph is defined as the average rate of change of the function over that particular interval. Now, remember, y2 can also be written as f of x2. They're the same thing. And y1 can be written as f of x1. And in this case, it's actually more appropriate to use this notation because the vertical axis is not called y, it's called f of x. So we use this notation here. So the average rate of change of a function on a particular interval is the slope of the secant line going through those 2 points, which we notated as m, the slope of a line. We call it m. We learned that in my beginning algebra course. And it's y2 minus y1 over x2 minus x1, but if we change to the function notation, then we have f of x2 minus f of x1 over x2 minus x1. So I know that seems pretty complicated, but we're going to figure out how to do this. It says if f of x is equal to this expression, what is the average rate of change of the function per unit x from x equals 1 to x equals 4? So we're looking for the average rate of change of the function, and we can call that whatever you want to call it. I'm just going to call it m. We can say m subscript AVE. That is going to be the slope of that purple line. But remember, we have a function here, so instead of calling this y value y2, we'll call it f of x2, and the other one f of x1. So f of x2 is going to be the y value with the second x value plugged in. And the other y value is f of 1. And then x2 is just 4, x1 is 1. So I know this seems kind of confusing, but that's why we're doing this, is to get used to this type of notation. So f of 4 is just this expression with 4 plugged in for x. So we have negative 4 to the second power plus 8 times 4 minus 14. And so that's f of 4, and then we're going to subtract f of 1, but we have to use parentheses. So we're going to write the same exact expression except with 1 plugged in. So we have f of 4, sorry, my computer's going slow, f of 4 minus f of 1 over 4 minus 1, which is 3. And then we just simplify. So this problem doesn't give us the y values. It only gives us the x values. So in order to calculate the difference in y, the change in y, we have to actually plug in these x values into our function. So that's what we did here. So let's do our final calculations. We have negative 16 plus 32 minus 14 minus negative 1 plus 8 minus 14 over 3. And if we add all this up, we get 2 minus negative 7 over 3. So we have 9 over 3, which is 3. So the average rate of change of the function over that particular interval, x equals 1 to x equals 4, is 3. So that means we change the y value by 3 units for every 1 unit that we change x. Very, very important concept for the study of calculus. So let's try one more of these before you try one on your own. So the average rate of change of the function on the interval x is equal to negative 2 to 2 is just the slope of that purple line. So remember, our slope formula that we learned in beginning algebra is y2 minus y1 over x2 minus x1. And that's the same thing as g of x2 minus g of x1 over x2 minus x1. So x2 is 2 and x1 is negative 2. And so we're going to plug in 2 to this function. So we want to calculate g of 2. So that's going to be negative 2 to the second power plus 8 minus negative 2. That's g of 2 there. G of negative 2 is negative 2 to the negative 2 power plus 8. That's g of negative 2. Then we're going to divide all that by 2 plus 2. And let's double check and make sure this is all written correctly. Looks correct. So now we can do the calculations. So we have negative 4 plus 8 minus negative 1 over 2 to the second power plus 8. We're using exponent rule number 8. Remember, if you have a negative exponent, it goes down into the denominator. The expression goes into the denominator of a fraction. And that's all over 4. So then we have 4 minus negative 1/4 plus 8 all over 4. And so we're out of room, but don't panic. We can use an arrow. So now we have 4 minus 7 3/4 over 4. So 4 minus 7 3/4 is going to be negative 3 3/4. Now it's easier to deal with a complex fraction when we have improper fractions rather than mixed numbers. So I'm going to change this to an improper fraction. That's going to be negative 15 over 4. And there's a lot of different ways to deal with complex fractions. A lot of different ways to think about it, but remember, this fraction symbol can be considered a division symbol. Long story short, we should get negative 15 over 16. Okay, so I want you to take a picture of we'll take a picture of all this information. And you can use number 20 to help you, so try number 21. When you come back, we'll do it together. Okay, we're back. So the average rate of change of the function in this particular interval here is 1. So y is changing by 1 for every 1 x unit. So if you got that right, good. Go ahead and try number 22. You can take a picture of these problems if you'd like to help you. Try 22. When you come back, we'll do it together. Alright, we're back. So the average rate of change should be negative because the secant line is going downwards, if you can see that. So if you got that right, good. So now we're going to do some more practice with function notation, because what we're about to do really requires a fluency in the function notation. So remember, in previous classes we defined a function and then we asked to find expressions relating to that function. So here we are asked to find f of r. Well, that would just be 2r minus 3. So we did that in previous classes. That's pretty easy. But now we're going to do something a little bit more complicated, because instead of asking you to find f of b, we're asking you to find f of 2 times b. So what does that mean? Well, that just means you're going to plug in 2b instead of x. Instead of your input being x, your input is going to be 2b. That's all it is. This is very easy. So we can simplify. Multiply those. 2 times 2b is 4b. There you go. So now we're going to rewrite the same thing that we have up here, except we're going to write m plus 5 instead of x. That's all that means. So we have 2m plus 10 minus 3, which is 2m plus 7. Now things are getting even more complicated, because we're asked to find f of x plus f of x squared. Well, f of x is just the exact same thing that we see up here. It's no difference. But f of x squared is the exact same thing that we see up here, except instead of x, we have x squared. And then if we want to simplify, we can write 2x squared plus 2x minus 6, because we can combine the negative 3's. So there you go. Alright, so let's try another one. We have a function g of x, and we're asked to find g of kp. So what this means is that we just write the exact same thing that we have up here, but instead of x, we write kp. So very easy. So let's try another one. We're going to write the exact same expression that we have up here, except instead of x, we're going to write 3x plus 5. We still have the absolute value symbols. And now things are getting a little bit more difficult, because we have two different expressions for the functions. This expression here is just going to be the exact same expression you see there, but again, instead of x, you have t cubed plus 4v. So that is this expression here. Now we're going to subtract. Actually, I put a plus sign. That should be subtraction. We're going to subtract the same exact expression, except we're going to plug in negative 6t instead of x. So this expression is there, and this expression is there, and that negative symbol is what's in between. Okay, so let's go on to one more of these problems before you try one on your own. So we're asked to find h of p over 2, given that h of x is equal to this expression. So we have p over 2 minus 5 over p over 2 plus 3 plus log base 3 of p over 2. Now this is a complex fraction, and that can be kind of tedious to have to simplify, but the easiest way to do it really is just to multiply both sides of the fraction by 2, and then you get p minus 10 over p plus 30 plus log base 3 of p over 2. Whoops, that should be 6, not 30. I don't know why I wrote 30. That's why you have to double check everything that you do. It's very easy to make a mistake. Okay, so now let's find h of b plus 5. We're going to write the same exact expression that we have to begin with, except instead of x, we're going to plug in b plus 5. So we plugged in b plus 5 here and here, and also here. So the numerator is going to simplify to b, and the denominator is going to be b plus 8. And there's nothing we can really do with the logarithm. There's nothing we can simplify. And that is the answer. So now we're going to find h of a minus 10 plus h of a to the 6th power minus 1. So let's first find this expression. We're going to copy this exact expression, except instead of x, we're going to write a minus 10. So I wrote this expression here. Then we're going to add this expression. So we have a to the 6 minus 1 minus 5 over x plus a to the 6 minus 1. Whoops. That'll be a to the 6 minus 1 plus 3, excuse me, plus log base 3 of a to the 6 minus 1. So we wrote h of a to the 6 minus 1 here, and we wrote h of a minus 10 here, and we have the plus sign in between. So now all we have to do is simplify, and we can't combine those logarithms because they have different expressions inside them. So we have a minus 15 over a minus 7 plus log base 3 of a minus 10 plus a to the 6th minus 6 over a to the 6 plus 2 plus log base 3 of a to the 6 minus 1. So there you go. Okay, so I want you to get a picture of this information here at the right. And I forgot to rectangle that problem. And I want you to try number 26. And when you come back, we'll do it together. That one may have caused a little trouble. If you had trouble with that, that's okay. So, if you got that right, good job. Try number 27. When you come back, we'll do it together. Okay, we're back. So this is just one way to write the answer. We could change the form again, but however you want to write the answer, I don't really care. That's not the point of these problems. So if you got that one right, excellent. Okay, so go ahead and try number 28. We'll do one more of these before we go on to the last thing we're going to talk about today. When you come back, we'll do it together. Okay, we're back, so there you go. If you got that right, good job. So now we're going to something called the difference quotient. And the difference quotient is basically exactly the same thing that we did in previous problems. But this is an expression that you're going to see in calculus so many times that you need to be familiar with it. So we're going to find the slope of the secant line in a particular interval, but we're going to use different notation. We're going to call this x value x, but we're going to call the other x value x plus h. Because in order to get this x value here, we're adding h, the distance from here to here, to the previous x value. So if we add h to this x value, obviously we're going to end up somewhere over here, assuming that h is positive. So this notation is very confusing. Now, if the x value of this point is x, then the y value would be f of x. Remember, f of x is just the y value of the points on the graph. Now, if the x value of this point up here is x plus h, then the y value would be f of x plus h. Now, I know what you're thinking. You're thinking, why are we making this so complicated? Well, this is just the notation that is used in calculus textbooks. So this point here is x, comma, f of x, and this point is x plus h, comma, f of x plus h. So the x value here is x, the y value is f of x, the x value here is x plus h, and the y value is f of x plus h. So if we want to find the average rate of change, that's going to be the slope of the secant line, which we call m, y2 minus y1 over x2 minus x1. And if we plug in these expressions here, y2 is going to be f of x plus h. That's the y value up here. The y value of this point is going to be f of x. That's y1. And the x value of this point up here is going to be x plus h. And the x value of the other point is going to be just x. So y2 is f of x plus h. y1 is f of x. x2 is x plus h. And x1 is x. We're just using different notation to label these points. And this special expression that we use for the average rate of change is called the difference quotient. It's just the average rate of change written in a different way. So notice that the purple x here and the green x just cancel out. X minus x is 0, so you're just left with h in the denominator. So we have this final expression here. Again, we call it the difference quotient. Now, why do we care about this? Well, this expression is used in a formula that is the foundation of the entire calculus curriculum. So it's a pretty important expression. I just want you to be aware that sometimes instead of h, the expression delta x is used. So notice down here we have h. We have a different form of the quotient where we use delta x. Delta x means change in x. In science and math, delta always means change. It's a Greek word. So we're going to learn how to use this notation, but we're not going to use the delta x notation because we don't want to confuse things. That gets a little bit more confusing. So it says here, for each function, find an expression representing the difference quotient. Use h for change in x, and it's not necessary to simplify the expression, so don't worry about simplifying. So I'm going to label the difference quotient as dq. The difference quotient is f of x plus h minus f of x over h. That's always the difference quotient. So you can get a picture of the information at the left if you want to, so you can refer back to that. Okay, so we just need to find an algebraic expression. Now, here's the procedure. This is the difference quotient. We're looking for an expression representing that difference quotient if f of x is equal to this expression. The denominator does not change. You're just going to rewrite it h. Very important. This expression is just whatever f of x happens to be. So we just copy that in there. So far, everything seems pretty easy. But f of x plus h is the part where students generally have some trouble. But it's really not difficult. F of x plus h is just the exact same thing that we have up here, except instead of x, we write x plus h. So this is f of x plus h. I was writing a little small there. Okay. And we could simplify that. We could definitely simplify. But the problem tells us specifically not to simplify. Okay, let's try another one of these. The difference quotient is f of x plus h minus f of x all over h. Again, let's start with the easy part. H we just rewrite. Just always rewrite h. It's just the same thing. F of x is exactly what that expression is up here. We were told that f of x is 2x squared minus 1. So that's the easy part. The hard part is when students have to find f of x plus h. But it's not really difficult if you know the language, the notation, what it's asking you. It's just asking you to write the exact same thing that we had for the yellow expression, except instead of x, we write x plus h. And again, we could simplify that expression, but we don't need to. Okay, so let's try another one. So the difference quotient is f of x plus h minus f of x over h. It's always that same expression. There's different ways to write it, but this is the way we're going to write it in this course. So again, let's do the easy part first. We just copy h, that doesn't change, and f of x is just whatever it tells us f of x is equal to. But f of x plus h, that's the part that students have trouble with. So we're going to rewrite the exact same expression, except we're going to write x plus h. Whoops, I forgot my plus 1. Plus 1 there. Okay, so let's try some more of these problems. I want you to get a lot of I want you to see a lot of examples of this before you try these on your own, because these problems can be very confusing. So we're going to do the easy part first. The easy part is to write h, then we're going to write f of x, that's f of x. So that's the easy part. Now comes the hard part. We have to find f of x plus h. So we have 1 over x plus h minus 3 plus log base 2 of x plus h. I move this over a little bit. So again, the reason that I'm using these colors is to show you where each expression came from. Very important for you to understand this function notation, and you're going to become more and more fluent with the function notation as you move up and up in the math curriculum. Okay, so let's try some more of these problems. Again, we need to try a lot of these before you try one on your own. So the difference quotient is f of x plus h minus f of x over h. Let's do the easy part first. So we're just going to rewrite h, and then f of x is just going to be exactly what that expression tells us that f of x is equal to. So that's the easy part. But f of x plus h is the part where students have a little trouble. We're going to write the same exact expression, but instead of x, we're going to plug in x plus h. So I know that this doesn't seem like it's that difficult now, but trust me, this causes a lot of problems in calculus. So let's try another one of these, the difference quotient. Again, it's the same expression. So h, we just copy that same expression down, and f of x is just x plus 10. And f of x plus h is x plus h plus 10. So I guess I didn't need so much room there. Alright, so again, we can simplify these expressions, but we don't want to do that in this course. We'll leave that for calculus. It's not that you can't simplify the expression, it's just that it's not really necessary. Okay, let's try another one of these, the difference quotient. Again, it's equal to the same expression. So let's do the easy part first. The easy part is just to copy h and to rewrite f of x. And let's try to make some more room here. So this is f of x right here. Now f of x plus h, again, that's the hard part. We rewrite the exact same expression, but we replace x with x plus h. And we need a little bit more room here. Then we have -4 times x plus h. Sorry, we're kind of running out of room here. So there you go. So there's another example. So try not to let this negative bleed into the fraction there. Okay, so let's do a couple more of these before you try it on your own. And we'll rectangle that. Now we just have f of x is equal to x. So how do we do this? Well, again, we're trying to find the difference quotient. It's the same expression. Let's do the easy part first, which is h. We just rewrite h. F of x is just whatever f of x happens to be. And f of x plus h is the same thing as f of x, except instead of x, you plug in x plus h. So again, we could simplify that, but the problem says that it's not necessary to simplify in these particular problems. So let's do one more of these. The difference quotient is equal to f of x plus h minus f of x, as we talked about, over h. Let's do the easy part first. We're going to rewrite h. And then we're going to rewrite f of x, which is just x plus 1 over x minus 2. F of x plus h is the same expression that you see up here. It's the same expression that we wrote in yellow, except instead of x, we're going to plug in x plus h. I guess we didn't really need so much room there. So that is f of x plus h. So I know this seems like it might be easy, but trust me, when you try to do this, you're going to find that it kind of plays with your mind. And so it takes a lot of practice to really make sure that you have this language down. So I want you to take a picture of these pages, and you can use numbers 31 through 37 to help you do number 38. Attempt number 38. When you come back, we'll do it together. Alright, we're back. So that is the difference quotient. So if you got that right, excellent. Go ahead and try number 39. When you come back, we'll do it together. Alright, we're back. So, there you go. If you got that right, excellent. That is the difference quotient. Go ahead and try number 40. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 41. When you come back, we'll do it together. Alright, we're back. So if you got that right, excellent. Go ahead and try number 41. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Try number 43. When you come back, we'll do it together. Okay, we're back. Okay. Go ahead and try 44. When you come back, we'll do it together. Alright, we're back. So there you go. So again, we can simplify these expressions, but that's not really the point of this. We can wait until calculus to simplify these expressions. We don't have to do it in this class. So if you got that right, go ahead and try number 44. When you come back, we'll do it together. Okay, we're back. So the difference quotient, again, is the same expression. It takes some while to get used to this. Some time to get used to this, so it's all about practice. So you got that right, excellent. Try number 46. When you come back, we'll do it together. Okay, we're back. So that's a complex fraction, but again, we don't have to simplify. The problem the problem set tells us specifically that we don't have to simplify. So if you got that right, good. Try number 47. When you come back, we'll do it together. All right, we're back. The difference quotient is equal to, again, f of x plus h minus f of x over h. It's the same expression again and again. So there you go. You got that right? Excellent. That is the difference quotient. Okay, so go ahead and try number 48. When you come back, we'll do it together. All right, we're back. So there you go. If you got that right, excellent. So again, that's the difference quotient. Okay, that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10, and don't go before you get the homework. Remember, the homework is not optional. Here's screenshot number 1 of the homework, and number 2, and number 3, number 4, number 5, and here's the answers to the homework. Remember, it's not enough to just attempt the homework. You must do it correctly. So get a screenshot of those answers. Do that homework completely, correctly, neatly, and keep it in order in your binder, and I'll look forward to seeing you in the next class.